There's a service document that Toyota quietly updated in 2021, not a recall, not a headline, just a revised oil viscosity recommendation buried in a technical service bulletin that most owners and even most dealers never saw. And when you understand what changed, and more importantly why it may have changed, it raises a question that a lot of Toyota turbo owners need to be asking about their own vehicles right now. Here's what keeps coming up in forums, in independent shop data, and in teardown videos. Toyota turbocharged engines running the factory recommended oil spec are showing consistent wear patterns, starting around 130,000 to 145,000 miles. We're talking about the 825A FKS found in certain RAV4, Camry, and Venza models, turbo bearing journals showing abnormal scoring, piston ringland deposits that look like varnish, variable valve timing actuators gummed up with residue that shouldn't be there at those mileages. These are engines that, on paper, should last well beyond 200,000 miles. And in naturally aspirated form, same block, different application, they often do. So what's different? The turbo. And what feeds the turbo? The oil? Now, before we get into the spec itself, I want to be clear about something. This isn't about blaming Toyota or calling anyone a liar. This is about understanding a mismatch between what an engine was designed to tolerate and what a manufacturer recommends for fuel economy and regulatory compliance. Those two things aren't always the same. And in the case of these engines, the gap between them may be costing people thousands of dollars in premature repairs. To understand why this matters, you have to understand what happens inside a turbocharger. Specifically, what happens to oil the moment you shut a hot engine down. When you're driving hard, boost pressure is up, exhaust temperatures are climbing, and the turbo shaft is spinning somewhere between 100,000 and 200,000 RPM. The oil film between that shaft and its bearing journal is your only protection. It's not a thick cushion. We're talking about a film measured in microns. Now you pull into your driveway, you shut the engine off, and the oil pump stops. The turbo shaft is still spinning, still radiating heat. But there's no longer any pressurized oil flowing through it. That residual heat soaks into whatever oil remains in the bearing housing and starts breaking it down. This is called heat soak, and it's why oil coking, the carbonized varnish-like deposits that form when oil degrades at extreme temperatures, is one of the primary failure modes in turbo engines. The thinner the oil, the less thermal mass it has, and the faster it breaks down under those conditions. Toyota's current recommendation for several turbocharged models in the North American market is 0W or 16. That is an extremely thin oil. To put that in perspective, 0W20 was already considered on the thinner end of acceptable for turbo applications by many independent engineers. 0W16 is a full viscosity grade thinner than that, and it exists primarily for one reason: fuel economy. Thinner oil creates less hydrodynamic drag on rotating components, which translates to measurable improvements in fuel consumption, improvements that help manufacturers hit government fleet economy targets. That's a legitimate engineering goal. Nobody's inventing that. But the question worth asking is whether those fuel economy gains come with a durability trade-off, and at what mileage that trade-off starts to show up. Here's where the technical picture gets more specific. Viscosity is measured in a few ways, but the one that matters most for turbo protection is HTHS, high temperature, high shear viscosity. This is the measurement of how thick your oil remains when it's being sheared between two metal surfaces, moving at high relative speed under heat. It's the number that most closely reflects what your turbo bearing journal experiences under load. 6. MPAS for passenger car applications. Most 0W20 oils land right around that threshold. 3 MPAs. That sounds like a small difference, but in a turbo bearing journal running, at 150,000 RPM with exhaust temperatures above 900 degrees Celsius a few inches away, a 12% reduction in oil film strength under shear is not insignificant. Think of it this way. You know the difference between olive oil and water? The way olive oil clings to a pan versus the way water just sheets off? That difference in behavior under heat and motion. That's what viscosity is capturing. When you thin your oil down in service of fuel economy, you're moving it closer to water on that spectrum. For most of an engine's operating conditions, that's fine. But for a turbo bearing at high load, high temperature, with intermittent oil starvation during heat soak events, you're removing a margin that was there for a reason. When you look at used oil samples from these engines, submitted to labs like Blackstone or Oil Analyzers Inc., a pattern emerges that's hard to ignore: iron and aluminum parts. Per million readings in 0W16 samples pulled at 5,000-mile intervals from high mileage turbocharged applications are running consistently higher than comparable samples from the same engine families using 0W20 or 5W30. Now, elevated wear metals don't automatically mean catastrophic failure. Some metal transfer is normal, especially during break-in. But when you're seeing iron numbers above 15 to 20 ppm at standard drain intervals on engines past 100,000 miles, and engines that should be in their stable wear phase, that's telling you something is accelerating. There's another marker worth paying attention to in these analyses: kinematic viscosity at 100 degrees Celsius, 0 centistokes, 8 centistokes. That's meaningful viscosity shear. The oil is losing its structural integrity faster than it should. And here's the compounding problem. Most of these owners are changing their oil on 5,000 to 7,500 mile intervals because that's what the dealer told them, and because the oil life monitor said so. The oil life monitor doesn't measure viscosity. It estimates degradation based on driving patterns. In a turbo application with a lot of heat cycles, it can overestimate the oil's remaining useful life. Now, Toyota has a response to all of this, and honestly, it's not unreasonable on the surface. Their position is that the 0W16 specification meets all relevant API and ILSAC certification requirements, that the engine was designed and validated with this oil, and that the improved fuel economy directly benefits consumers and supports emissions compliance. They'll also point out that modern engine tolerances have tightened considerably, and that many contemporary turbo designs are built to operate with lower viscosity oils because the bearing clearances and oil delivery systems have been optimized accordingly. Those are fair points. Tight tolerances do reduce the amount of hydrodynamic drag oil has to overcome. An API certification isn't meaningless. It represents a baseline of quality and performance testing. But here's where Toyota's own documentation starts to work against their recommendation. Because when you compare the North American spec sheet to what Toyota advises in European and Japanese markets for the same engine family, you get different numbers. In several European markets, Toyota recommends 0W20 as the standard fill for turbocharged A25A applications, with 5W30 listed as an acceptable alternative. That's a direct contradiction. Same engine architecture, different oil recommendation. And the explanation isn't altitude or ambient temperature. Those factors would push you toward thinner oil in cold climates, not thicker. The European spec is thicker. There are a few theories about why this discrepancy exists. One is regulatory. European fuel economy. Measurement cycles historically penalize viscosity less severely than the EPA's test methodology, which means there's less financial pressure to use the thinnest possible oil in those markets. Another is legal exposure. European consumer protection frameworks in several countries make it somewhat easier to pursue warranty claims related to design decisions, which may make manufacturers more conservative in their published specifications. Neither of those explanations reflects anything about what oil is actually best for the engine's longevity. They reflect what oil is best for the manufacturer's position in a given regulatory and legal environment. When you understand that, the TSB update from 2021, which modestly revised service interval language without changing the base viscosity recommendation, starts to look less like an engineering improvement and more like incremental positioning. So what does this actually mean for you? And more importantly, what should you do if you're sitting at 80,000, 110,000, or already past 140K? If you're under 80,000 miles and still under powertrain warranty, stick with the factory spec. Using a different viscosity during the warranty period creates an opening for the manufacturer to complicate a potential claim. What you should do is shorten your oil change interval. Instead of 5,000 to 7,500 miles, go 4,000 to 5,000. The additional oil changes cost you maybe $150 a year. A turbo replacement on one of these platforms runs $2,300 to $4,000 at independent shops, more at the dealer. If you're between 80,000 and 120,000 miles and out of warranty, this is the decision point. Many independent shops and a growing number of Toyota specialist mechanics now recommend transitioning to 0W20, specifically a full synthetic that meets or exceeds Toyota's WS specification. Not 5W30, not high mileage formula, not conventional. A quality full synthetic 0W20. The modest viscosity increase provides a better HT/HS buffer without meaningfully changing cold start behavior or creating any compatibility issues with engine seals. The difference in fuel economy is statistically negligible in real-world driving. We're talking fractions of a mile per gallon. If you're past 130,000 miles and you've been running the factory 0W16 spec at standard intervals, do a used oil analysis before your next change. Pull a sample at your current drain point and send it to Blackstone or a similar lab. It costs around $30. The results will tell you your actual wear metal numbers and your oil's remaining viscosity. 0, you have evidence that the oil is breaking down faster than the engine is comfortable with. That data should inform your decision about whether to step up to 0W20 and whether to cut your drain intervals further. Regardless of your mileage, here's what you can do this weekend. Pull your dipstick, wipe it on a white paper towel, and look at the color and consistency. Fresh synthetic oil is amber and transparent. Oil that's breaking down under thermal stress goes dark and starts to develop a slightly gritty or thickened texture at the edges of the sample spot. It's not a scientific test, but it tells you whether you're way overdue on a change, and it gives you a rough baseline sense of how hard your engine is working the oil. The broader lesson here is one that applies to any turbocharged engine, not just Toyota's. The factory specification is the manufacturer's answer to a multivariable optimization problem, and longevity is one variable among several. Fuel economy requirements, manufacturing cost, regulatory compliance, warranty period cover a GE, they all get weighted. The factory spec is designed to get the vehicle through its warranty period with acceptable reliability. Whether it's also optimized for 200,000 miles is a separate question, and one the manufacturer has less financial incentive to fully address. If you're running one of these Toyota turbo platforms and you've been wondering why your engine sounds different past 120K than it did at 60K, or why your oil looks unusually dark at short intervals, this is worth digging into further. Drop your model year and your current mileage in the comments. I want to see what people are actually experiencing out there. And if you've already done an oil analysis on one of these engines, share those numbers. The more real-world data we can put together, the more useful this conversation gets. Subscribe if you want to catch the follow-up. I'm going to go through the specific early warning signs that these engines show when turbo wear is progressing, and what the repair options actually look like at different stages. That's the practical side of everything we covered here today.